Okay, so if you remember, for a piecewise function, um, we have at least two parts, two pieces, where for a certain value of x, we define the function uh, differently. And I think I should use the term domain. That's more convenient if you're already familiar with that. So for different part of the domain, the function is defined differently. If you're wondering what is a domain by any chance, domain is the values of the independent variable for which the function can be defined. I mean, or rather is defined, I would say. Okay. For example, if I say uh, f of x equals to x squared, so that's a function. Now, what could be the uh, values of x for which the function could be defined? Anyone? Oh, thanks. Someone is in the waiting room. Okay.
Is that
Anyone?
like all real numbers or something like that?
And why do you think like that?
Maybe excluding zero, maybe. I don't know.
Yeah, you're actually right. So by the way we define a function mathematically, um, it actually gives me the idea that it has to be possible to see that, or it is possible to actually draw the graph, you might say, graphically. If you're representing graphically, you might say that it's possible to graph it. Or if you are trying to find a value, it will be possible to if you input that value, it will be possible to find the corresponding functional value. If it's possible, then we say the function is defined at that value. So f of x equal x squared, if you take any value for x from the real number line, from negative infinity to infinity, not including infinity though, any value, whether it's a zero, it's a whole number, it's a fraction, it's a decimal, whatever it is, it's a negative value, whatever it is, if you input any value for x, for f of x equal x squared, you will actually get a value, won't you? So we say the domain of this function is all real numbers. That means for any value of x, the function could be defined. So I would rather use the word domain from now on. If you have any questions about domain again, just let me know once we finish. Um, we can chat via Zoom or even in the email thread. So uh, I'm going to use the word domain from now on. Okay. So for for different parts of domain, as you can see for this graph, although there is a hole at x equals 2 and x equals 3, we actually have a different value at x equals 2. And can you see what could be the value? If you just go straight to the y-axis, you can see, as my cursor is moving, you can see this value is actually 5. Can you see that? So that means we say this function has, or rather is defined for any value starting from 0 to 6 other than 3 and 2, or 2 and 3, and at 2 we have a different part which is a straightforward 5. Okay, now we don't need this too much in our concept. Let's continue from where we left. And in the next slide, as you can see, okay, all right, so here is how you can see which value approaches, I mean, which value gives you the functional value. So for x equals 1, you can see if you just go vertical, this way, you can see it's going to this point. Now, if you go to your left horizontal way, you can see the functional value is 2, right? At that particular point, the functional value looks like it's approaching 2. Can you see that? So that means we say, from the graphical representation, by the way, we say that f of 1 equals 2. Like the way I have said in the previous slide, that for x equals 2, our functional value is 5. The same way, right? We went straight up to this point at 2, and then we went to our left to see where does it actually approach, right? So we say it's approaching towards 5. All right. Yeah, here you go. In the next slide, we have it. F of 2 equals to 5. So since we can see at 2, we have a defined value here, this black circle. And then if we go to our left, we can see it's actually approaching to 5. Okay, now what happens to the limit? That's what we are most concerned. We're not really concerned about the functional value too much. Yeah, we do need this, but we're actually concerned about the limiting value. Where does it approach? Okay, so for limit, we actually approach from 2 ways, 2 sides, by the way. So we approach from the left and we approach from the right, and we see where does it take us? Where is it heading towards? Okay, let me show you the next graph. Where is that? Oops. I think I should use this graph. Yeah. Okay, so now let's forget about the functional value and all that. I just want you to answer, if you approach from the left, I mean this way, just look at my cursor. If you start from the left and approach towards 0, approach towards 2, x equals 2, this way, okay? I'm repeating. If you approach from the left towards this point 2, where does your graph take you? Can you see that? Your graph actually takes you to this, slowly and slowly, slowly and slowly. It's taking you to this point. Can you see that? If you approach from the left, this graph also approaches towards this. Right? Do you agree with me?
Yep.
Yeah.
So we call this is the left-hand limit. You will soon see the definition. I'm giving you the initial idea of it. Excuse me. You'll soon see the mathematical definition of it with some algebraic characters and all that. So if you approach from the left, wherever the graph takes you, we call it the left-hand limit. Now, similarly, if you approach from the right in this way, slowly and slowly towards 2, you'll see the graph is slowly and slowly going towards this, right? As you're approaching towards 2, your function, or rather your graph, is approaching towards this, right? So we call it as the right-hand limit. Okay. The most interesting thing is, not always you will see the graph is approaching towards the same point for a particular value of x. On this occasion, whichever direction you are approaching from, at 2, you'll see the graph is actually approaching to the same point, which is 3. Can you see that? You can see the pinkish dash. This dash line signifies that this particular hole is actually at 3. And you can see, doesn't matter which way we are approaching from, this function is moving towards 3 from either direction, right? At x equals 2, of course. So you will see more examples. I guess in most examples, you will see that it's approaching towards the same point, but you will definitely see some examples as well, where if you are moving from the left, it will approach to some point. If you move from the right, it will approach to some other point. You will see some examples of that as well. So it's not like that it always moves to the same point, okay? But fortunately, since this is the first example, they have made it so that it looks good, so that it doesn't become awkward in the first place. Okay, now why do you need this? Okay, so for that, I want you to see that definition first. Okay, yeah, okay, and we'll come back to the graph again. So the right-hand limit, if f is defined for all x near a with x greater than a, and f of x is arbitrarily close to L for all sufficiently close to a with x greater than a, we write limit x tends to a plus. This plus means you are approaching from the right. So this notation is really important, because in the question, in the homework or even in the exam, you will see this plus or minus sign. There will be nothing in English that will say that you are calculating the left hand limit or approach from the right or something like that. Nothing like that. It will only have this plus or minus sign. This plus sign will lead you uh, to that point from the right, and this negative sign will mean that you need to calculate the left hand limit. So you need to understand this. I don't want you to memorize this. If you just understand what does it mean, that should be fine. This plus mean you are approaching from the right, or in other words, you are calculating the right hand limit. And for minus, you are approaching from the left. That means you are calculating the left hand limit. Okay, left sided limit. Okay, they have defined this as left sided and right sided. Okay. Uh, Now, what does this x greater than a mean? Okay, now let's go back to the graph. So here, oops, not this one, yeah, this one. Here, our a was 2, since we are approaching towards 2, right? So this a is the value where we are approaching to, from either side, doesn't matter which side we are from. So on this problem, a is 2. Now, what does x greater than a mean? Or on this occasion, x greater than 2 mean? That means you are considering the value on your right. Because on the graph, the more we go towards our right, the bigger the number is, the bigger the value is, and vice versa for left. If we go to our left, the value is actually getting smaller, right? So this x equals x greater than a means you are actually going to your right, and that's what we need for right sided limit, right? Because we'll be moving from the right hand side, so obviously you need to consider the values which are greater than the value you're approaching to. Now, does this make sense before I move any further? Anyone, any question?
Just a question. So going back up to your graph where a is equal to 2, when you're considering all values that are greater than 2 in that graph, does that does the whole at 3 come into play or no?
Yeah, that's a good question. So fortunately, we have one more condition here. The whole has actually an important role, but fortunately, you can see all x near a.
Okay.
So that means we actually don't need, precisely, we don't need all these values. We actually need the values near to, although it will be the same result, even if we start from in positive infinity or positive 6 or positive 5. The result will be pretty same, or not pretty same. It will be exactly same. But since we have a hole, we can actually get rid of it by saying that we are starting from here, right? We want to go that further. We can start from here and then slowly and slowly go towards 2. And it still will give us the same thing, because it's this part, this little part is also greater than 2. It's we are also moving from the right, and it's also approaching 2, so it's still satisfying the conditions. Yeah, that's a good question.
When you say near, is that like what we were talking about yesterday, where it's like you had infinite zeros and then a 1 to it?
Yeah, exactly. You can actually consider that. Yeah.
Okay, cool.
Yeah. So since we can't really, mathematically we can do that, but since we are visualizing, or since we are hand calculating this, we can't really add too many zeros, right? So instead, what we do, we start like this, say 2.9, 2.8, 2.7, 2.5, 2.2, something like that, right? It's still near A and near 2 on this occasion. It's still more than 2, and we're approaching from the right. And since we are approaching towards 2, you can see the functional value is approaching towards this hole, which is at 3, right? Okay, so that's what the definition gives us. Yeah. And what would be the right-sided limit then? Right-sided limit would be just the functional value at that point. So why is that? Yeah, here we go. So we are approaching towards 2 from our right, and the function is approaching towards this. And we know this value is actually 3. So we'll say the right-sided limit when x tends to 2 plus is 3. Do you agree with me?
Yeah, that's correct.
Again, go back to the definition. We don't want to go too fast. We want to clarify this before we move further, okay? Because this is the basic you will need moving further. Things will get more and more complicated. So if you don't clarify this now, then things might get more complicated, okay? So here you can see limit x tends to a plus. On our problem, we had x tends to 2. So we'll say limit x tends to 2 plus. That means we are moving from the right, and at 2, or rather when you're approaching to 2, someone in the waiting room, just allow me to add him. Yeah, okay. So if you're approaching to 2 from the right, your function f of x was approaching towards 3, right? We have seen this in the graph, and that value is going to be our right-sided limit. As you can see, if f of x is arbitrarily close to L for all x sufficiently close to A, with x greater than A. So f of x is arbitrarily close to this point, which is 3, right? Where x is obviously greater than A, which is 2 on this occasion, for this part. So we say this is the right-sided limit. Sorry, I'm late today. I could not get my laptop to connect to the Wi-Fi today. No problem. No problem. Okay. Now let's see the left-sided limit. It's actually the same. You can clearly understand, but on this occasion, we'll be moving from our left. So all the x will be less than that value, less than A, right? And you can clearly imagine, because we'll be approaching from our left, and on the real number line, we know the more we go towards left, the less, I guess, the value gets smaller and smaller, right? So it will be definitely less than what we have on our right. So if we go to our left, I mean, if we approach from the left, those values will be definitely less than this, right? So it's the same thing, the same idea. Now we'll see what happens. See, we are approaching from the left towards 2, right? And this functional value is approaching towards that hole again. So f of x is arbitrarily close to this L, which is 3, for all x less than 2. So we say it's the left-sided limit. Now, any question from this? Anything which is kind of creating confusions?
So what about the 2, 2, 5?
Yeah, I will go to that, but we are not yet to that particular point. We are actually approaching towards that too. We still didn't say anything about what happens at 2. We'll actually go to that. Yeah. If you're approaching from the left and if you're approaching from the right, then what happens? That's what we have seen right now.
Why would you specify which, if you're going to the same point, why would you specify which way you're going from? Is it just the tangent line changes?
Okay, so that's a good question. I think the reason is quite simple. Since if you move from your left and move from your right, you'll see some problems that you will actually reach to 2 different points. You know, this looks obvious to you because these 2 points are actually taking you, or rather these 2 approaches are actually taking you to the same point, which is which is 3. But you will see, as I said, some examples where if you move from your left, you'll reach here, and if you move from your right, you'll reach somewhere here. I mean, you'll reach 2 different points. That's why we need to know, if we approach from either side, where does it take us?
Okay, that makes sense. This is just not a good example of that.
Yeah, I think this is the first example, I believe. So I think they try to keep it simple, because if they start with uh, um, an example where 2 approaches take you to 2 different places, then things might look scarier in the first place. So maybe they have adopted this since this is the first example. I think we have one example in this particular slide. I think so. I think, yeah, here you go. As you can see, we'll actually come to this after a while. And you will see, if we approach from 2 ways, it will actually take us to 2 different points. Yeah, that's a good question again. Yeah,
Oh
anything
yeah,
else?
that makes sense. Thank you.
Anything else? Because this is something really, really basic, yet it's tricky. You will see examples which will which might blow your mind when you first see that. When you just eyeball it, you might wonder, oh my god, what's that? And if you ever feel that, no worries, that is the most common case. Okay, so don't get demoralized. I'm not trying to scare you. Rather, I'm trying to say that it happens, and it will happen probably at least to half of you, and no worries. Okay, but any question from the definition, or how did we actually define all this? There are so many characters here: x greater than a, f of x is close to L, x tends to a plus, a positive, whatever you say. So many things to take care of here. Any questions from this? All good? Okay. All right, let's move to our next slide. Okay, so let's say this is our graph of the function f of x equals x cubed minus 8 over 4 times the quantity x minus 2. Okay, now first of all, we want to know why does this two graph look different? Because you can see there is a hole here and this looks like having no holes. So what is the difference? Which one is correct and why? Okay, so we'll go back to the definition of domain. Okay, I think, yeah, this is going to be very handy. I didn't think like that. Yeah, but the idea of domain is also very important here. Okay, so don't look at the uh, graph, don't look at what we have in the box, just look at the function, okay, and try to imagine a value of x for which you will not get a defined value. Can you imagine a value of x which gives you an undefined or infinite value? You might say it's actually not infinite, but often we say uh, that it's infinity. It's giving us infinity. So we say we don't have a defined value. Can you imagine any value? If you just plug in that value in place of x, you don't get anything in return. Try to imagine. Just spend 10 seconds on this. Don't look at the graph or what we have inside the box, okay? Just plug in, for example, if you plug in x equals 0, in the numerator we have 0 minus 8, which is negative 8. Yeah, could you please repeat it?
Yeah, it's gonna be 0. When we plug into x raised power 3, it's gonna be 8. 8 minus 8 is 0. The denominator is gonna be 0 also.
X equals what? Sorry.
The numerator is going to be 0.
For which value of x?
Yeah, x raised to power 3. When we substitute 2 inside the x raised to power 3, it's going to be 2 raised to power 3 is going to be
X
8.
equals 2,
So 8
exactly.
minus,
Yeah, that's right. X equals 2. So we actually don't care about the numerator. The shortcut is when you have a fraction, you just need to see for which value of x the denominator is getting 0. We are just concerned about it. If numerator is 0, that's fine, because the numerator 0 over something gives us a 0, and that's still a defined value, so no worries with that. But we don't want the denominator to be 0, because that gives us undefined value, right? There will be no defined value for that. So clearly you can see if x equals 2, then the denominator becomes 0. Can you see that first of all? Then we move further.
yes.
So if x equals 2, then 2 minus 2 gives us 0. So the denominator becomes 0 and the functional value overall becomes undefined. So we say that for x equals 2, we don't have a defined value. Okay. So that means there should be a hole at x equals 2. Doesn't matter how the graph look like, but we don't have a defined value at 2. That's what we definitely know by just eyeballing the function. We don't care about the graph. We can clearly eyeball it and see that for x equals 2, we shouldn't have a defined value. There has to be a hole or something like that, a break. There has to be something. It can't be continuous. It can't go straight away over the point x equals 2. And so this one is actually wrong, this graph on your left, because you can see for x equals 2, the graph is still going on. There is no break, nothing at all. It's a straight line. So this is not right. Whereas for this one, you can see at x equals 2, there is a hole. That means we don't have a defined value there. So clearly, out of these two, this one on your right looks like the right graph. So wherever you have an undefined value, you need to have a hole there. You need to have a break there. Okay. You can't have a value, a functional value for that point in the graph. If the function itself says that there is no defined value at that point. Okay. It will make more sense once we see some more examples. But before that, we want to do, or rather repeat the same process, which is going from our left and going from our right. So don't look at what we have written here. Just try to approach from your left and approach from your right and see where does it take you. Okay. So if you approach from your right, for all the x's which is greater than 2, I mean, we are approaching towards 2 again. You can see the graph is approaching towards this hole, which is taking us to 3, right? And if you're approaching from the left, the graph is approaching towards this hole again. So again, your left-sided limit and right-sided limit is 3. So here is a suggestion for you in the exam or even in the homework. There could be 2 types of question. The first one could be calculate the left-sided limit or calculate the right-sided limit with where the function will be given, or there will be no function. The function will not be given, only the graph will be given, and still you will be asked to calculate this. That means a graph will be given and the question will ask you to find the left-sided limit or the right-sided limit. So what you need to do is you just approach from your left and see where does your graph take you, and repeat the same for the right-sided limit if it's been asked. Okay, so you could be given a function and asked to calculate the limit, or you could be given a graph and asked to find the limit. Okay, you will soon see more examples of it as well. Let's see one.
Mr. Ek, here's my question.
Yeah, sure.
From the slide 10, please, can you move it back from to the slide 10? Okay. So based on the graph as a case study, does it mean that when the graph is moving from the right, does it mean that we can say the value of x is 2.5 from the graph? I mean, from the right.
Oh, no. They're not trying to signify any particular value of x. It's not 2.5 or 2.6 or anything in particular. What they're trying to do here by drawing this pinkish dash, I'm sure you're talking about this, right?
Yes.
Okay, no.
Because when I'm looking, because as I'm reading the graph from the right, it's the x is behind the 2. Then from the left now, the x is in front of the 2.
So it doesn't need to be any particular point precisely. If you're just moving, they're trying to show that this x, whatever this x is, this is actually greater than 2. Do you remember? If you remember the definition, there you go. This x had to be greater than that value which you're approaching for. So this is trying to signify that. It's not really trying to point out anything precisely. For example, 2.5 or 2. It looks like 2.4 to me anyway, but it's not trying to point out that precisely. It's trying to show that you are approaching from the right, and since you're approaching towards 2, the values you're approaching, the values of x, when you're approaching 2 are greater than that. That's what it's trying to show.
Okay.
Nothing else.
Okay. Thank you.
Mhm. And obviously, it's also really, really close to 2 as well. That's why they have drawn this. You don't need to do this though when you are um, uh, solving it in your exam or even in the homework. You don't need to draw anything. You can just eyeball it and draw the conclusion. I mean, write the conclusion. Okay. Okay. Now, does it actually make sense? We just can verify it. You don't need to though in your exam or in the homework, but we can actually verify that whether the graph actually is taking me to the right solution. Am I doing it right? So if we approach towards 2, you will see that it actually is taking you to 3. Can you see the table? You can see when you're approaching from the right, it's slowly and slowly getting reduced and slowly going towards 3. And again, if you're approaching from the left, smaller values than 2, you can see it's slowly and slowly getting increased and trying to reach 3. If you have more points here, let's say 2.0000001, you will see this value will be more close to 3. Same goes with this one. If you have 1.99999, like 7 or 8 nines, you will see this value is more towards 3. So when you're approaching towards 2, the functional value looks like that it's approaching 3. So that means our graph gives us the right solution. Although again, I'm repeating, you don't need to verify this. You don't need to waste time on this if, of course, you are confident enough that you have done it right, because you can see this will take some time. If you start verifying this, it will definitely take some time. I don't think you should do that unless you are confused that whether you have done it right or not. Okay. All right. Now, why do you need that for finding limit? Okay. So if I say find the right-sided limit, you can do that. Don't bother about the left-sided limit, or vice versa. If I say find the left-sided limit, don't bother about the right-sided limit. Just look for the left-sided limit. Okay. Don't worry about the other approach. But what if I say find the limit at that point? What if I say that? That means I'm not mentioning which way you are approaching from. I'm saying that tell me where does the function take you if you approach towards 2. If I go back to the graph, this one. Now I'm saying when x tends to 2, that means when x is approaching towards 2, where does your function take you? I'm not saying you anything, say anything precisely. Which way you are approaching from? Now what should you do? Any guess? Anyone? Because if I say approach from the left, you can do that. Or if I say approach from the right, you can do that as well. What if I don't mention anything? What if I just say find the limit when x tends to 2?
Find both.
Okay, good point. Yeah, find both. And then what if it's different? Well, on this occasion it's same. I know it's the same. It's taking us to the exact same point, which is 3. What if it's different?
That
Wouldn't
not
that-
be like the true limit, I
Sorry.
guess.
Sorry. Do you please repeat it?
You said if they don't reach the same point, is that not the true limit?
Exactly. Very good point. So that's why we need these two for finding limit. That means if your left-sided limit and right-sided limit is equal, then we say that limit exists at that point. I mean, when you approach that point. If it's different, we say limit does not exist. Or you might even in short format, you might write DNE, does not exist. I don't mind if you use shorter format, just as long as you use it in a proper way. So that means it's really important, especially when you are calculated the limit, not left or right sided. If you are just calculating the limit, that means first of all you need to find the left sided limit, then you need to find the right sided limit in any order, doesn't matter. And then if those values are same, then you will say that the limit exists and the limit is actually that particular value which you are getting, since that's the same, right? And if those values are different, you say the limit does not exist. That's what the definition, or rather the theorem says. Assume f is defined for all x near a except possibly at a, then the limit is L if and only if the left hand limit is L and the right hand limit is L. That's what I actually said. That means the limit will be the same value, will be the value which you are getting from the left and right sided limit, but those values have to be same. If it's different, you say the function does not have any limit. Okay, and obviously at that point, yeah. Any question? Yeah.
Like an example of this, like
Yeah, sure, of course, we'll definitely do that. But I think we should go for the next one. Yeah, we should go and we should try this one, and then we'll go back to the definition. Okay, so you don't have anything now. Now, if I say find the right-sided limit when x tends to, or if x approaches to 1, can you calculate it for me by just eyeballing the graph? X approaches to 1, then what is the right-sided limit? Just eyeball.
Would that be like 1.00 or 0012, or it would be, well, it wouldn't be 2, it'd be like 1.999. So it'd be 1.0001 comma 1.999, right?
No, you are just looking for the value, by the way. You don't
Oh,
need
okay.
to show all this, right? So if you just approach from the right towards 1, you just need to see where does your function take you. Can you see where does your function take you?
-2.
-2, exactly. So the right-sided limit is -2. Now, please let me know if you have any confusion about it, anyone, because I'm repeating, this is going to be really crucial. This is really important, and it's tricky, you can see. Is there anyone who is still confused why the right-sided limit is -2? Don't hesitate. I'm more than happy to rediscuss it. Take your time, okay? Take your time and see if you have any question. Anyone? Any confusion? Why did I say that the right-sided limit for this function is -2?
So will there always be a point where we'll stop at when we're following that line
I
for the
didn't,
limit?
I didn't get your question. Would you please repeat it?
Oh, yeah. Will there always be a point that we'll stop at? How there's a point at -2? Will there always be a point where we know to stop at for the limit?
Yeah, I think you're right. We can actually find a limit for any point, but you will see the question will ask you to find the limit where there is a break or where you need to stop. Yeah, I think you had a fair enough point, but the truth is you can actually calculate it for any point. You know, it doesn't need to be, just give me a second. Someone in the chat wrote something. Does every graph have a right and left sided limit? Okay, I'll come back to that question. Okay, yeah. So we can actually calculate it for 2 as well. I mean, when x approaches 2 as well, we can actually do that. But yeah, in the question, I have seen the questionnaire generally tells you to find the graph where you need to stop or where there is a break or hole. Yeah, but you can actually calculate it for any point. We can actually calculate it for x equals 2 as well. Maybe we should do that, but let me first solve it. Now, if you have no other question, who can tell me what's the left-sided limit of it?
2.
Caitlin, I'll come back to your question, okay? Bear with me, but let me finish it first.
The left side of the limit is 2.
Anyone else?
Yeah, 2.
Yeah, 2.
Anyone has still confusions? How did they reach 2, or why they are saying the left-sided limit is 2? Anyone? Okay, so let me clarify this once again, and then I'll answer some questions. So you are approaching from your left, right? So you are approaching this way towards x equals 1. So slowly and slowly your graph is approaching this way. And you see, when you are going close to this one from left, this graph is going close to this hole, which is at 2. So we say that the left-sided limit is 2. Same way, the right-sided limit is -2, because we are going to 1 from your right, your graph is going this way. So we say the right-sided limit is -2. Now a quick question. What should be the limit of this function when x tends to 1, x approaches 1?
It will still be -2.
Anyone else?
What's the question?
Okay, let me repeat that. So now the question is a really quick question. When x approaches 1, what is the limit of this function g of x?
Isn't it undefined because there's 2 limits?
Exactly, very good. So our definition says, if you remember, those left-sided limit and right-sided limit have to be equal for the limit to exist. So when I say x approaches 1 and you are trying to find the limit for that, we have actually 2 different limits. For left-sided limit, we have 2. For right-sided limit, we have -2. Those are different values. So we say limit does not exist when x tends to
Okay.
1.
Okay, can we say it is undefined too?
I think the right choice of word should be does not exist rather than undefined. I
Okay,
think we should
had it
be more
been
precise. Yeah, sorry.
Had it been the graph on the x-axis, the graph is due across 2. That's how we can trace it to that's how it is easy for us to trace it to -2. What if the graph is drawn across 1?
I didn't get your question. Would you please repeat it? Maybe it's because of the background noise. Would you please
If the
say
graph is
it
drawn,
slightly louder, maybe?
okay. If the graph is drawn on 1 instead of 2, how can we, if there's a shift from 2 to 1, I mean the graph is drawn on 1. Do you get what I'm saying?
You are saying that there is a shift on 1. Do you mean this one?
Yes, if the graph is drawn on 1, which technique we can use to trace the limits?
I'm not still getting your question though, but if I'm getting it right, you are saying that if I somehow find a graph which is reaching that point one, I mean, there is a shift here, there is a defined value here, right? That's what you're saying, there is a defined value for one.
Yes.
Okay, so doesn't matter whether we have a defined value at one or not. We need to have the same value for the left-sided limit and right-sided limit. For example, I'm just adding this, although this is not here. Let's say at one, the function has a value which is positive one. Okay, there is a black. Imagine a black circle here at one. Okay, just at where the cursor is pointed. So at one, there is a defined value for this function, which is one, but it still doesn't give us any limit because still the left-sided limit and the right-sided limit is different. It has to be the same. If you have a defined functional value, that actually adds nothing to the limit. Even if you don't have a defined value at that point, we can still have the limit. Okay, but the necessary condition is to have two same values for left and right sided limit.
Okay, thank you.
And to answer your question, Kathleen, yes. Sorry, no, we might not have left-sided and right-sided limit for all the functions. So for some functions, you will see we don't have the left-sided limit. For some functions, you will see we don't have the right-sided limit. So it doesn't necessarily mean that we'll have both-sided limits, for all the functions. Yeah, that's a good question. We'll see some examples where we won't have a particular side. Okay. Okay, now let's take a break for 5 minutes. Okay, we'll come back at 10 or no 10 12. Yeah, come back after 5 minutes. And meanwhile, if you can go over those discussion, you already have these slides. Go over this again, and if you have any question, if you can generate any question, we can start with those first. Okay, once we return after the break. Okay, see you in 5 minutes. Okay, we're back. Now, did you find any question you want to ask? Anyone?
This, I don't know if it's really pertaining to this. It kind of is. Is there like any other mathematical like formulas that we need for limits, or is it just looking at graphs to find it, or is there's a
So,
way to find it using?
yeah, good question. Yeah, you will see some formulas as well. Yeah, but not now. Uh, the limits we are trying to find now doesn't need any formula, but yeah, you will see um, some formulas to find the more complicated ones. Yeah, definitely. Okay. So I think we should go for the next one. Am I going too fast? Just slow me down, okay? If you think like that. No worries, I won't mind at all. As I said, I'm a student, so I can clearly understand what you are going through. And I'm more than flexible to make any adjustments, okay? If you think I'm going too fast, just let me know. Just say, hey, hold on, give a break, or just slow it just a little bit, okay? I'm more than happy to do that for you. Okay, all right, so. Okay, let's see an interesting example now. So this is the graph of cosine 1 over x. Okay, don't get scared. It's actually been shrinked so that um, um, you can kind of visualize why, or rather what happens uh, when you have a graph like this. Okay, the graph actually doesn't look like this. As I said, it's been, the intervals have been uh, really shortened to see what's actually happening there. Okay, so first of all, what we want to see is what happens if you approach to 0 for this function cosine 1 over x. Let's say we haven't seen the graph. Okay, we'll eventually go there, but let's say we haven't seen the graph of cosine 1 over x. We want to see mathematically where does it take us if we approach to x equals 0. Okay, now if you approach to x equals 0, that means you are going really close to that, right? That means let's say if you're approaching from the right, it will be, oops, someone has entered the waiting room now. Really? Okay, anyway. All right. So you will start with a value, let's say, let me use this, use the previous graph, not this one. Yeah. So you are approaching towards 0, right? Not this graph, by the way, I'm just showing the real number line. So you'll start from somewhere here, right? And go slowly and slowly towards 0 to see where does your graph take you, right? So you can start with 0.001 or even with 0.1, then 0.01, 0.001. If you start doing that, you will see, you will get some different results. I mean, it's not really converging. It's not really going towards a particular value. You can see for some values, you are getting something positive. For some values, you are getting negative. Now, what is that? What does it signify? What can we, what is the information we can derive from it? Sorry.
That
Oh,
there isn't one, that there isn't a limit.
Yeah, exactly. So first of all, we can say that if we approach to 0, well, we shouldn't say there isn't a limit. Maybe there is another technique, there is another formula, but definitely we can't conclude this way. That's for sure. We can't reach any conclusion. For example, if we just try the first three, let's forget about the other three. Okay, if we just try the first three in the braces, you can see it looks like it's going towards -1, isn't it? Doesn't it rather? Because you can see it's -0.95, then it's -0.99. So it's slowly and slowly getting to -1, right? So we might conclude after doing these three steps that this is taking us to -1. But hold on, the fourth one is a positive value. I mean, when you approach more towards towards 0, you will see no, the functional value is actually not taking us to -1. So this gives us an idea that we can't conclude this way. For most examples, for many examples, if we approach this way, for example, it's the most naive approach to start with. If you somehow forget the formula, if you somehow don't remember how to do it, you might do that. But the irony is it will not give you the right solution all the time. And that's what we have seen here. Does it make sense? We're still not sure whether the limit exists or not. We'll try to find it soon after. But now, as of now, we can see we can't really conclude, can we? Because it's giving us different results, and even the next one gives us negative, something negative, and the next one gives us a value which is actually quite going to going quite away from -1. So it's not really giving us an idea, a genuine idea what should we do. So we can't really do that. And now the graph will make more sense. You can see since you are approaching towards 0, let's say this way, you can see it's actually moving up and down like this. For some values, it's going to +1. For some values, it's going to -1, and so on and so forth. So that means the values of cosine 1 over x actually is oscillating between -1 and 1. Can you see that? Any question from this? Just try to eyeball this. Just imagine this, okay? Use your intuition. And since you're going to more towards 0, you can see the graph is actually taking you, once it's taking you to 1, once it's taking you to -1, that means it's oscillating between -1 and 1. Can you see that?
So in this case, because you can't find the limit for 0, would you, if it's asking for a limit on the graph, would you have to just find a different point on the graph to find that limit, or can you just write in it's not defined?
Yeah,
Or-
you can clearly write it does not exist. Yeah, definitely, because you can't define a particular value. It has to be same, at least, if there is any, but we can already see that it's taking us nowhere. If the graph looks like this, then you can say, yeah, the limit does not exist. Okay, let's go to the next slide and see what more information you can see. Oops, okay, 2.3. Okay, now we have the techniques for computing limits. Okay. All right. So the first one, as I said, you will have several formula, some, I guess, at least 4 to 5. I'm not sure how many this book has added because there are so many, but at least 4 to 5 basic formula to find or to calculate limit. The first one is the most obvious one and the most, and I should say The easiest one is the limit of the linear function. Now, the first question would be again, what is a linear function? Don't look at the theorem, don't look at anything. Just try to imagine, or rather start with this. What is linear? How do you define something linear? The linearity of something. What does that mean in English, maybe, not in maths?
Something that is moving straight.
Sorry,
A straight line, something that is straight, moving
straight.
on is yes.
Yeah, very good. Straight. Yeah. Anyone else?
Continuous.
Continuous. Okay. A continuous function could be nonlinear.
Follows kind of like a set pattern, I would guess. It doesn't necessarily have a lot of changes in its shape or any.
Will you please repeat it? I think I missed out something.
Follows a set pattern, arguably has no changes in the direction or shape of the line.
Yeah, very good. Yeah, definitely. Definitely. So for the linear
increment doesn't
functions,
change.
yeah, sorry.
Oh, I was just saying the increment doesn't change at all.
Yeah, that works as well. Yeah, very good. That actually is the other way of saying that your shape is not changing or your direction is not changing. Yeah, very good. So if you have a graph and you can see it's going straight, it's not really changing its direction, it's not curvy. That means it's a straight line going to the same direction starting from the word go. Right from the word go, it's actually going to the same direction, no break, or I shouldn't say no break. There is no curve, no change of direction, no change of increasement or anything like that, just going straight. So that is graphically, you can say it's linear. How does it look like algebraically? So the algebraic format is this: mx plus b. Now, what is the m? M is actually the slope. You remember the slope, the word slope? We actually discussed it the last time, I guess yesterday. Yeah. This M is slope. Now, what is the slope? Anyone?
The rise over change in y over the change in x.
Change in y
Very
over
good.
change in
Yeah, yeah, very good. So that's actually the ratio of the change of the y values or the functional values over the independent values, whatever it is, or you might say rise over run. So that is the slope. And that b is the y-intercept. Now this could be a new term again. Is there anyone who understands this intercept, the concept of intercept?
It's where
yes.
it's where it crosses the y-axis.
Exactly. Yeah. So it's where the line intersects the y-axis. So starting from the origin to that intersecting point, the length is called the y-intercept. Okay. So this b is the y-intercept. Okay. Now this is the algebraic format of the linear functions. And if you have a linear function and you are asked to find the limit of that, what you can do, you can just plug in the value in place of x. That means if you're approaching to a, let's say x tends to a, then if you just plug in a in place of x, you'll get the limit, you'll get the value, limiting value. Okay, let's see one example of it. So many formulas. I like it. Oh, so they haven't added any example of it. So let me do it for you. Okay. So if I say f of x equals to 2x plus 1, the first question is it linear rather? Do you think it is a linear function?
Yes.
So
Yes.
if the function is 2x plus 1, that means it's a linear function. And let's say I'm saying find the limit when x approaches 0. So what should you do? Since it's a linear function, we can just plug in 0 in place of the x, and whatever we get should be our answer. So can you calculate it for me? I'm saying find the limit when x approaches 0 for the function 2x plus 1.
So 1 then?
Exactly. So if you just plug in 0 in place of the x, it means 2 times 0 plus 1, so it gives you 1. So the limiting value of the function 2x plus 1 when x approaches 0 is 1. So whenever we have a linear function, and that's a tricky one, by the way. I actually tend to do this. I'm actually giving you the question. I'm spoon feeding you the question. I have done this. As I said, I was a TA for Calc 1 for 3 semesters. So I actually did it quite a few times. I actually gave them a linear function, and trust me, most of the students tried all these formulas, even though it was not necessary. You could have just plugged in the value which you're approaching for in place of x or whatever the variable is, and that's it. So when x tends to a for a linear function, just plug in a in place of x. That's it. Isn't
And
it
so
interesting?
for our answer, it'll just be left in that form, like an equation, or how does that?
Your final answer?
Like, say if it was on like a test or something like that.
Okay, so if it's a multiple choice question, or if it's a really short question for one point, you can just write 1. I mean, it was 1 for the question I've asked, right? Is it? Yeah, I think so. So you just write the answer. But if it's a question where it's written show your work, then you need to show these 3 lines here. That means first write limit x tends to 0 for f of x, sorry, 2x plus 1, then write equals to f of 0, then write 2 times 0 plus 1 equals to 1. I mean, show your work. How did you do that? Otherwise, you can just straight away write the final answer.
Okay.
Okay, any other questions? No questions at all? All good? Okay, let's move on then. And again, if you have any question, even after we finish, just let me know, okay? Because this is really basic, and you will surely need this once we move forward for the more complicated ones, okay? Okay, here you go. So now just fasten your seatbelt, and let's see how can we cope up with this, okay? Don't get scared, but if you have seen this, that's even better. But if you haven't, no worries. We'll try to go as deep as possible for each examples. 2.4, 2.3. Okay, yeah. So we have 4 here and 7 here. So I guess 10 to 11 formulas anyway. All right. So for each of the each part of the theorem, I'll try to give you at least one example. Okay, let's start with the first one. Okay, so when you have two different functions, the limit of the sum of those functions is actually the sum of the limits. That means if you find the limit individually and then add those, you should get a result. Okay, that means for two different functions, if you add those two functions and get the limit for the sum, it's actually the same as getting the limits for each of those functions separately and adding those. Now let's do one example of it. I wish I could share the iPad. Okay, let me do it this way. Let me leave it for tomorrow, because I think I should show you examples of it. What do you think?
You said examples tomorrow, or?
Yeah, I think you need to see at least one example of it, because I don't think without the examples it will make sense. I don't think so. You need to
Are
see.
you in the Zoom call on your iPad too?
Sorry?
Are you in the Zoom on your iPad?
Yeah, I have Zoom, but if you remember, yesterday I joined with that as well, and there was so much echo that I was not able to talk.
I think if you mute one of them but have the speaker on the other, it should be okay.
I had done that. Let me try it one more time, okay?
Well, also there should be a whiteboard sharing screen in Zoom.
Yeah, in my Mac, it gives me the chance of screen mirroring. It's really easy, but in the Windows version, and this laptop is not mine either, it's not letting me do anything. So yeah, let me try joining again. I hope it will work, because I need to show you examples. Okay. Okay, I'm trying. Meanwhile, let me go over. I don't want to waste any time, so I can do two things simultaneously. So the first one says, as I said, if you add two functions and find the limit of that sum, it's actually the same as finding limits of two different functions separately and then adding those two. Okay, now what does this mean? Let's say I have a function f of x equals 2x and g of x equals 3x when x tends to let's say 0. So what it says, if I add those two functions first, so if I add 2x and 3x, it gives me 5x, right? And when x tends to 0, can you find the limit for me for 5x when x tends to 0? Anyone?
Is it 0?
0, exactly. It's a linear function, first of all, because it's in the form of 5x plus mx plus b, so that is 5x plus 0. So it's a linear function. For the linear function, I can straight away plug in the value which we are approaching towards rather, in place of x. So it gives me 0. Now let's try the right hand side. So it says I can find the limit separately and add those. So when x tends to 0, f of x was 2x. What's the limiting value of 2x when x tends to 0?
Would it be 0 again?
0 again, yeah, it's again a linear function, and it gives me 0. Same goes for the other function as well. When x tends to 0, the limit of 3x is also 0. And if you add those two, 0 plus 0 is still 0. So that means it's giving me the same thing. Okay. Okay, now I'm trying to share the screen. Can you see the screen of my iPad?
Yeah.
Yes.
Perfect. Okay. There you go. Okay. I actually had it ready for yesterday, but couldn't connect it. So let's do it for today. Fortunately. Okay, yeah. So let me show one example of it. So again, I can't really share two screens now. I'm not sure whether I'm actually allowed to do that, but if you have the slide in front of you, that would be nice. Okay, you can see the screen, and I can show it on my iPad. Does that work?
Yeah.
Okay, so have that open in front of you. So the first one, it says limit of two functions. Let me write it for you first. If you add two functions, and get the limit, it's actually equal to this. That means find the limit of these functions and add those. Okay, now let's see the example. So let's say f of x. Let's try one complicated one now, since we have the iPad now. So let's try 7x minus 3, and let's say g of x is 3x plus 5. Okay, we're just trying with the linear one. We'll try more sophisticated functions once we see the non-linear ones. Okay, so first thing we need to do is to add this for the left hand side, right? Pardon my bad handwriting. So if we add this, 7x minus 3 plus 3x plus 5, I'm just adding these two functions, okay? So it gives me 10x plus 2, right? Do you agree with me? Now I'm going to take the limit of it. Limit x tends to, let's say, 1 of f of x plus g of x equals to limit x tends to 1 for 10x plus 2. So it's, since it's a linear function, I can straight away plug in 1 in place of the x's, right? So 10 times 1 plus 2, which gives me 12. Do you agree?
Yeah.
Okay, now let's do it for the right hand side. So limit x tends to 1 for f of x, which is limit x tends to 1. What of the function again? 7x minus 3. 7x minus 3. Since it's a linear function, we can straight away plug in again. So 7 times 1 minus 3, which gives us 4. And similarly, limit x tends to 1 for g of x. Limit x tends to 1. The function was 3x plus 5. 3x plus 5. Again, we'll plug in 1 in place of x. That gives me 8. So if we add these two, f of x plus limit x tends to 1 g of x. It gives me 4 plus 8, 12, and it is the same. Oops, sorry. It's the same as this. So this proves the theorem. Any question from this?
So on the exam, can we do it either way?
Yeah, exactly. That's why the theorems are here. So if you see a function where you can use this theorem, you are more than welcome to do that. Yeah, definitely. All the theorems we'll see from now on, you can definitely use this whenever it's convenient. Whenever you actually can. You can't really use it if it's not applicable, but if you can definitely, and I think you should definitely use it, whichever formula, whichever theorem works. Okay. Yeah. Any other questions? All good. Should we go for the next one?
I had a question. So we plugged in 1 because it's as the limit approaches 1, right? Earlier you said we were using 0 just because it was a linear function. Do we, for solving these as linear functions to find the limits, do we always use what the limit is approaching then?
Yeah, exactly. Whatever you are approaching towards.
Okay.
Right. Yeah.
And I'm guessing that you would supply what we're going to.
Yeah, definitely. Of course. Because as I said, you can actually find it for any value of x. It might does not exist, but you can definitely calculate it. I mean, whether it exists or not, if it exists, what it is, you can actually calculate it for any value. And this function, for example, could be calculated for x tends to 2, x tends to 3, for anything. So yeah, it will definitely be given. No worries. Okay. Okay, so let's go to the next one. All right. Okay. Where is the next one? I think it's for the difference. Did his audio cut for anyone else? Really?
Yeah.
Yeah, your audio cut out a little bit when you were explaining that
Okay,
you
which
that
part do
it's-
you want me to re-explain?
basically you were talking about how like the you can find this for any x value,
Mhm.
and your audio cut out.
Oh, I think then you didn't miss out anything. It should be fine. Okay, sorry about that. That's why I really hate this online class, but that's how it is. Anyway, I remember one class, in my graduate study, the professor, I had a meeting with professor for some particular reason, and I was trying to log in, and then my computer started taking setup. Can you believe it? And the professor was kind of furious because he had to wait for 12 minutes. You know, the Big Macs, it takes time to get updated. And he was really furious. And from that day, I generally tend to start at least 10 minutes earlier for each meeting. Anyway, that's a good lesson. All right, so the next one is for differences, right? So this one was for sum of two functions, or it could be, okay, good point. I think I should say this is not really for only two functions. This theorem could be used for any number of functions. I mean, if you have 4 functions or 5 functions where you can add this and get the result, it actually works for those as well. It doesn't necessarily mean that it has to be for only 2 functions. Okay, you can use this for any number of functions. No problems with that.
would the question ask, like, would it be written as f of x plus g of x in the problem
No,
to know
no.
that you need to add them, or how do you know that you need to add them or
Very
subtract?
good point. Very good point. Yeah, the question will probably not ask you. I'm planning to avoid it. It will not ask you to uh, use this formula. You can even solve one problem without using a theorem, but these theorems definitely make your life easier. So whether or not you use it, it depends on how good you understand or how well your concept is based on the topics we have. So it will not be mentioned. I'm pretty sure that I'm going to avoid mentioning that. There could be,
So
yeah, sorry.
will you explain, like, I guess, how would you know how to use them, or?
Yeah, definitely. I guess, let's say, uh, not for this one though, but for some other properties, I think by just eyeballing, you might understand which formula can you use. I think, yeah, I think let's try to see one example each. And meanwhile, if I can see one example which can be used for this purpose, I'll use that. Otherwise, I need to generate one very good example, because if I try to do that now, that might not be the best fit. So I think I should either generate it and show it tomorrow, or maybe we can find one, since we're going to do one or two more theorems today. Yeah, I think we have 15 more minutes. Yeah, we can easily do 2 or 3 more properties. Let's see. Yeah, you can definitely eyeball it, and it depends on the number of problems you do as well. The more you practice, the more your intuition will work towards it, even after, you know by eyeballing, just eyeballing, you might understand which theorem you can use, but for that you need to have some sort of experience of doing this. So hopefully I'll be able to show you that how does this work. Yeah, that's a good question. Okay, what's the next one? Next theorem. Who can read it for me?
It's the difference, and it's the limit of f of x minus g of x.
It actually works the same way. If I just remove this, it actually works the same way. Okay, yeah. It's basically the same thing. If you do that, it will give you the same idea. So if I remove this minus, it will be minus. So I'll have 4x minus 8. If I subtract the functions I have, I get 4x minus 8, right? So now let's do that. I'm just using negative in place of the positive one, nothing else. Okay, so I have 4x minus 8. And I can still plug in the same value, which is 1. And I'll get -4. Do you agree?
Yes.
Okay, now next I'll find it. I already have this. This doesn't change because this is the limited value for 2 functions. We have found it separately, so that there is no harm in that. We just need to change this one. So it will be minus this, -4, and once again you can see it's the same. Do you agree?
Yeah.
Now, any question from this? You don't need to get overcompensated. by just seeing these obvious things. This looks easy and this looks obvious, but definitely this might be tricky sometimes. You'll see when we have more complicated functions to deal with. No questions at all?
I guess just to clarify, this is only for linear functions, right? These set of, or does it work for, other things?
These theorems?
Yeah.
It works for any function, yeah. Any given function, but yeah, definitely you can do it when you have more than one function, right? That's one of the things I should have said. Yeah, when you have more than one function to deal with, more functions to deal with, then you can use these theorems. If you have only one function, then it doesn't really make sense. Yeah. Okay, what's next? I think rather than asking you, I should go to the slide.
It would be constant multiple,
Okay. All right.
which is C f of x.
So I'm going to write it first for you. Do it 3, and it's limit extends to, oh, okay. So for the theorem, did I use a? Yeah, okay. All right. So extends to a, c f of x, c is any constant, okay, equals to c times limit of extends to a f of x. Now, what does this mean? This means if you have a constant with a function, whatever the function is, as a product, of course, what you can do, instead of keeping that inside your limit, you can bring it outside. You can bring it outside like this and find the limit of the function and then multiply those. I mean, you don't need to have that while you're calculating the limit. You can keep it outside, find the limit of the function, and then multiply this and find the product. You'll still get the same result. Okay, let's see one example of it. Oops. Okay, let's say, let's take a more complicated function now. Let's say limit x tends to -1 for 5 times x squared minus 1. Okay, let's try this one now. Okay, so what we want to do is, first of all, let's find the left-hand side first. I think I should have used a different color. Yeah, let's find the left-hand side now. If I do that, limit extends to -1. It's 5x squared minus 5. I'm just multiplying it, okay? No worries. Now, what should we do? Is there any way I can make my life easier?
Well, it's still a linear equation, right? So just go ahead and plug in your limit.
Why do you think it's linear?
It's not
that's-
actually because it's
that'll
squared,
be a
isn't it?
parabolic
Exactly.
Yeah.
function.
Exactly. It's not linear, but the good thing is you can still plug in the value. You can still plug in the value if the function is still defined for that. I think in that theorem they didn't mention it, but the truth is it's not only it does not work only for linear functions. Instead, it actually works for all the functions where plugging in the value keeps your function defined. So if you plug in the value here instead of x, it still keeps your function defined. Can you please unmute yourself? I don't know where the background noise is coming from. Yeah, thank you. Okay. So, but we'll not do that first. We want to use a property here. You don't need to, but I'm just trying to show how can you do that. Can anyone see anything that we can do here?
Wouldn't you be able to factor out a 5?
That was already here. I've actually found the product
Oh,
so that I can use property. I can use a theorem. Can you see a theorem I can use? What if I say I want to use the second theorem, the theorem of the difference? What do you think? Can I do that? Because I have two functions, right? I have two functions. So I can use the theorem. The theorem says, instead of finding the theorem, instead of finding the limit of these two, I can actually find it separately and then subtract it. See the theorem? I can find the limit separately and then subtract it. Do you agree? I'm just showing one example. How can you use that? Because again, it will not be given that you have to use it. Whether or not you use it, it depends on how do you see that problem. So let me use it first, and I think it will make more sense. So I can actually do this. 5x squared minus, just using the second theorem. Just a quick reminder, if you use any theorem, just don't forget to mention it in the side note that I am using this theorem here. So using theorem, what was the number again? 2.3 portion 2. Yeah. Sorry. Yeah, like this. So that's the theorem I have used. I can just calculate it separately and then subtract using just the previous theorem we have just seen. Okay, like this one. Now let's do that. So since it's keeping our function defined, we can actually plug in -1 here. So 5 times -1 squared. And since there is no x here, whatever, or rather, wherever we are approaching for doesn't matter. It will actually give us 5 always. So this will be 5 minus 5, which is 0. So that's the left-hand side. Let's do it for the right-hand side, where we have said that if you keep the constant outside and find the limit, it will still give you the same result. Okay, let's do that. So I'll keep the constant outside, find the limit of it. I think it will x squared minus 1, right? Yeah. X squared minus 1. Again, it's not doing any harm to our function. It's still defined if we plug in -1. So I can plug in -1 in place of x, So it gives me 1 minus 1, which is 0, 0. And as you can see, we have the same result. So that means we can use that. Whenever we have a constant working as a product, we can keep it outside and just find the limit of that function and then just multiply it like this. 5 times 0 is 0, so it doesn't make any changes, but we can definitely use this. Do you agree? Any question from this? Anyone, any question? No questions at all? All good?
Yep.
Yes.
Very good. So let's finish it here because we only have 1 more minute. Let me stop sharing the screen. Okay. All right. So for tomorrow, your pre-class assignment would be to go over the slide 2.3. Isn't it 2.3? I believe so. I think it's 2.3. Yeah, slide 2.3, the third slide.
Is that,
Sorry.
yeah, is that techniques for computing limit?
Sorry.
Yeah, the 2.3 is the section. The section 2.3 is techniques for computing limit.
Yeah, exactly. Techniques for computing limits. So what I want you to do is when we meet tomorrow, I want you to, and before that, I want you to go over this particular slides. Just try to see what they're trying to say. Just see if you can understand any of those. Just try to see if you can generate any questions from this. Nothing else. You don't need to do any assignments. It's a reading assignments, as I said. I'll make an announcement as well of it. So when you meet tomorrow, we'll start from here where we are ending today. But I want you guys to go over this, okay? All right, if you have any question, don't hesitate to send me an email. I'll be traveling to Laramie tonight though. But hopefully I'll reach safe and healthy, and we'll meet tomorrow at 9. Bye-bye.
Thank you.
Thank you.
Thank
Be
you.
safe.
See you tomorrow.
Have a safe flight.
Thank you.
I had a question for you.
Yeah,
real
sure,
quick.
sure.
Obviously, because my canvas is messed up right now with the, I don't have access to any of the files or announcements or anything from this class right now.
Mhm.
Is there a way that I could get the slides so I can read over them?
Yeah, do it this way. So I'm writing my email address in the chat. So just send me an email saying, hi, I'm Jack. Can you send me the files? And I'll send you, okay? Because I don't know the email address of you. So if you can do that, that would be nice.
No, of course I can do that.
Okay, so here is my email. Just you can copy and paste. Okay, did you get that?
Yes.
Okay, so just send me an email saying, hi, I'm Jack. Nothing else. I think I'll recognize you and I'll send you the files. No worries.
Okie dokie, I can do that. So thank you so much.
Bye.
Bye.